All right, so we're going to look at a problem that has change in elevation. There's some friction, kinetic friction, and there's a spring. So this is exciting. And we're going to, of course, apply energy conservation or what I call energy analysis to this problem. So our energy analysis equation is the overall change in mechanical energy is equal to the sum of the works done by non-conservative forces here, and just reminding us that the definition of work is the scalar product of force and displacement, and that works are done by forces. So that's the basis of our analysis here. So check it out. We've got this object just on the top of a hill here, height h, that's given. And then it's going to slide down. What we're assuming here is that this is all like frictionless interface, except for this one frictiony patch. So this one frictiony patch in here, we've got friction right in there. Apart from that, we don't. And everything needs to be really well defined in our problems, mostly due to our level and the math. We only have certain types of math we can use in this class. We don't have differential equations, so things have to be really well defined and somewhat a little bit simpler. But we can still work on skills here. So we want to find the maximum compression of the spring. So that'll happen the first time the block slides down. It'll go across the frictiony patch there. Some of our mechanical energy will go to friction there, right? And then the spring will be compressed through some displacement. And that's what we're asked to find is that compression. And then after it bounces off the spring, you can kind of imagine that it's going to go back across the frictiony patch and then the question is, how far up the hill will it travel? You know it's not going to get back up to a height h again, right? Because you know that some mechanical energy has been transferred to thermal via friction. But the question is, how far is it going to get? So let's just start out by looking at the first part of this problem here. And of course, looking at our energy analysis. So initially, we have this thing just sitting there. Let's assume that it is at rest on the top of the hill. And released from rest. So let's have that be one of our assumptions there. And so all of our energy initially is in the form of gravitational potential. And I can just write that out very nicely. And that's assuming that the lowest point in our problem is going to be my y equals 0. That's usually my advice. Choose the lowest elevation in your problem, call that your y equals 0, and measure everything upwards from there. So that is my initial energy. Now, okay, here's the question. What am I going to call my final? Well, right now I'm going to call this final the energy that's in the system when the spring is at full compression. Okay, so I know there's a lot going on here, but I'm really going to analyze here where the block is at top of the hill as my initial, and my final is going to be when the spring is at maximum compression. And when the spring's at maximum compression, the block is stopped, right? It's at its lowest elevation, so there's no gravitational potential energy. The block itself is at rest, there's no kinetic energy. So the only energy in the system is actually the spring potential energy. And this is what I'm going to call my max X. That's something that I'm being asked to find. So in this first initial, this is at rest, at top of hill, right? And then my final will be spring at full compression. And when that happens, think about it, the block comes to rest there, just like for that moment. But we have to pick which moments in time we're going to model here for our initial and final energies. And then the right-hand side of the equation asks me for work done by non-conservative forces here. So the only thing there, my non-conservative works, is going to be the work done by kinetic friction. So that will be my kinetic friction multiplied by my displacement multiplied by cosine 180 degrees. Okay, to know that, really what I need to do is, though, is draw my free body diagram. So let me look at this. So this is going to be, actually, you know what, I'm going to do this up here. The free body diagram when we're on the friction patch. Our brains like the pictures to kind of make sense physically. So let's look at this just during the friction patch here, right? So if I look at my free body diagram there, when the mass is going over the frictiony patch, what do I have? Well, I've got kinetic friction to the left, normal force upward, and weight downward. That's it. There's nothing else that's touching the block as it's sliding. And imagine right now we're imagining it sliding over this frictiony patch here, right? That's where we're imagining the block. The only thing it's in contact with is the surface beneath it. Surfaces can exert two types of forces, normal forces and frictional forces. We've considered both of those here. And then I get my one invisible force, which is weight. That's it. There's nothing else going on with this block. So when I'm looking for non-conservative forces, I can be reminded of my direction of displacement, which is going to be rightward here. I see that the normal force is again perpendicular to the displacement, so it doesn't contribute to work, doesn't do any work. Weight is a conservative force, so that's not a non-conservative work. So the only non-conservative work here is going to be done by friction. Cool. Okay, so I can flesh this out a little bit here. If I do, this is again the one spot I can do my Newton's second law analysis is in defining my normal force. Normal force is going to be equal to weight. In this case, we're on a horizontal surface and there are no other vertical surfaces acting, sorry, no other vertical forces acting, and I have zero acceleration in the vertical. So all those factors contribute to the fact that our normal force and weight are equal in this case. So this is going to give me negative mu k mg d. That's the work done by friction. Great. So this basically kind of wraps it all up there. So I can then take these three quantities and put them into my energy analysis equation. So this is going to look like, remember, energy final minus energy initial equals the sum of the non-conservative works. So in this case, it's going to look like 1/2 kx max squared minus initial energy, which is mgh, is equal to non-conservative works. In this case, it's only one work, mu sub k mg d. Cool. So that's one equation that I've rendered there. This question is asking me for the maximum compression of the spring. So I can look at this right now and ask myself, do I have everything I need in order to find the max compression of that spring? And I do here, right? The only thing I don't know in here is X max. So I can do the algebra and then solve for my X max here. And you should get something like 2 mg h quantity h minus mu k d. That's a d all over k. That quantity is to the 1/2 power there. Remember that x was squared in the equation. Okay, so we have just answered part A of this. So the second part asks us how far up the hill the mass is going to travel after it's compressed the spring once. And we have some choices here, like where or what are we going to choose as our initial and final energies for part B? It's up to you, I guess. What I'm going to choose as my initial is the spring when it's at full compression. So basically, what was the energy final for part A? I'm going to choose that as my energy initial for part B. So if I'm going to move on to part B here, what I'm going to say is my energy initial for part B, I'm going to prime that since it's different from my initial energy in part A there. That's the spring at max compression. So 1/2 K X max, which remember now I know squared. So this is the spring at maximum compression. And the idea, as you can probably tell here, when we're trying to express our initial and final energies or particular mechanical energies, we do that for points in the system that are well known, that are well defined. The spring at maximum compression is super well defined, and it's pretty easy to write out because there's only one type of energy, and that is spring potential. So my final energy for part B, I'm going to have that be when the block goes back up to um, its new maximum height, I guess you could call it. and it'll come to rest there at that new maximum height. So I'm going to call this MGH prime. So this is what I'll call the block at its new max height. And this is the max height. The new max height is what we're being asked to find in part B. The only work done by non-conservative force, again, is the work done by friction. And well, if you think about it, right, after the block goes from the max compression of the string up to its new maximum height, it has to go over that frictiony patch again, doesn't it? Yeah, so our friction here is going to be the same, mu k mgd. And at first you might say, hey, why is it going to be the same? Because it's going the opposite direction. So wait, let's go back. So, and you'd be right, like it is going the opposite direction. So you could ask yourself, what's going to be different about this free body diagram, right? So now we have like, here's the hill, the frictiony thing, and then here's the spring at the end, right? Okay. So now what we have is the block is going to be going through the frictiony patch this way, going to the left. So what does that mean about your free body diagram? You're still going to have normal force. That's the same. Well, your kinetic friction just flipped around, didn't it? Because it's impeding the motion. So now it's going to be pointing to the right. You still have weight. But guess what? Your displacement also switched. So now your displacement is pointing to the left. So I still have that 180-degree angle in between my frictional force and my displacement. So I'm going to end up with the exact same expression for work done by kinetic friction when I slide back. And this is a good reminder that like it's not dependent on how fast the block is going or, any of that stuff, how long it takes. Time isn't part of that. Okay, so I have this all done. I can then put this back into my energy analysis form. A reminder that form looks like energy final minus energy initial. These are primed here, is going to be work done by non-conservative forces, which is actually the same as as part A. So what does that look like? Final is mgh prime, our new height that we're after. Initial 1/2 k x max squared is equal to negative mu sub k mg d. Great. So now my job here is to solve for h prime. And I can do that, right? Remember that we now have an expression for x max, so I can sub that in. M, D, and K are all known. And h prime is then something that I can express in terms of known stuff. And it turns out kind of cool, actually, when you do substitute in for that you get a really elegant expression. So your algebra intermission, right? H prime is going to be equal to H minus 2 mu k d. So this is our final answer for part B. I really like it because it's really meaningful as far as the expression goes. You can see that, so H prime is going to be lower than or less than H as long as mu sub k is greater than 0. And I could say as long as D is greater than 0. But you have some choices here. Like, so if you're coding this, right, if the user put in a coefficient friction of 0, then you could see that the block would go back up to its original height. If the user put in D, like the size of the frictiony patch, the size of the frictiony patch is going to matter too. The greater D is, the lower that block is going to come up, right? Because the more that you're going to be subtracting away from the initial height. So that's true with the coefficient. If you turn that coefficient up and you make that stronger and stronger, then the negative term here in this final expression is going to increase, and that means your block will not go up as high after it compresses the spring. And that makes sense, right? So when you're looking at this final expression, it's kind of pleasing to see that that really makes sense. And if you have another thing that you can ask yourself here is what what would the outcome be where the block wouldn't even like make it through the rough patch, right? Is there an outcome where like it doesn't even make it through? Are there values that the user could put in if you were coding this where it stops and it doesn't even make it up the hill at all? Kind of interesting. Okay, anyway, hopefully that was a fun problem. A little more practice with energy analysis.